Students will recall how to find the gradient at a point using calculus. That's going to be really important today. Students will apply calculus and knowledge of linear functions as well as the definition of a tangent and normal to determine tangents and normals. And there's a massive variety. You might have noticed if you read ahead of my OneNote that I had some stuff written here that was actually a note to myself because I'm starting to write some complex unfamiliar questions for you. And this topic is really rich in complex unfamiliar questions. There's heaps and heaps of different ways we can ask questions that make them based on this content but hard. And so it is really rich in that respect. I didn't mean to leave that on the one that you had, but I've just deleted it and you probably saw it there. Anyway, here it is. This diagram represents what we're talking about when we talk about a tangent and a normal line. So if you're determining a tangent at a point, it will be the line that has the same gradient as the function at that point and goes through that point. Typically, a tangent is a straight line that kind of hits the curve and then continues on, doesn't go through the curve. That's typically what happens. But obviously you need to be a bit careful because the tangent line could look like, oh, this is not working. Oh. What happened before? The tangent line, the curve could look like this. And if the tangent line at, say, this point here actually goes through the curve. So it could go through the curve, so don't feel like it has to just bounce off. Depending on the curvature of the curve, it could. When you talk about tangents related to circles, they do just bounce off. The normal is perpendicular to the tangent. So this is a right angle, and the normal is perpendicular to the tangent, which means I have a gradient to the function at that point. The calculations here are pretty easy, but you've got to understand it's a little bit abstract and you won't walk away from this thinking I've learned tangents and normals and I know where they are applied in the real world. That won't happen because that's something for later on. Anyway, here we go. Some notes. Tangent at point x, y is a straight line that passes through point x, y and has the same gradient in the function. A normal at point x, y is also a straight line that passes through x, y, but is perpendicular to the tangent and thus the function. So if you're writing stuff down, I'm going to skip over that. You could write that down a bit later if you want to, leave about 4 or 5 lines, but that's basically what I've just paraphrased. But first, let's talk about an important process. And so this will come up not just in this topic, but it will come up a lot. And it's a process you need to recall from year 9 and 10. And that is how to determine a straight line from a gradient and a linear function. So it'll be really important. So I've got a bit of an example here. Let's say that a linear function has a gradient 7 and it passes through point 1, 5. So I've just made those up. If you want to practice this, you can just make stuff up. It works. If I have that information, step 1 is to recognise that we know the gradient. So in our standard linear form, y equals mx plus c, we can just take the m out and put 7 in. That's the first thing. We know that for sure. We just need to find our c value. To find a c value, there are going to be multiple ways you can do this. There usually is. But the way I think is easiest and best and works every time is to just recognise you have a known point. We've already put 7 in as our gradient. Put the known coordinate in. Solve for c. C comes out as -2. And there's our function. Y equals 7x minus 2. A really easy process. Massively important for this topic. And there will be questions on tangents and normals in the A2 exam. So you've got to make sure you know this. In fact, I can confidently say this will come up. It might come up even as a complex familiar, a straight up question. And if you can get this process right, we're talking 5 marks, probably maybe 6, just to do this process. So if you get to know it, it's easy marks in your exam. Here is this. I showed a few of you this last time because I'm excited by it. If you're pushing the boundaries and you want to do well, get the 90 to 100% mark, then doing the type of generalization I've done to get here is going to help you with that. So here is I've just done it with the quadratic. Up the top, you can see my generalized quadratic. And I've set up, and hopefully you know you can do this in Desmos, sliders for A, B, C, and also another value G. So I've set up G as just a floating point on my quadratic. So it's the X value of my floating point. And then I've done some background calculations, which you may consider later on when you're comfortable with this, to challenge yourself to try and set up the same thing to work out that my linear function for the tangent will be y equals 2a times the x value plus b times x plus c minus ag squared. That actually determines my tangent for whatever a, b, c, and d are for this quadratic. And I've got my normal calculation as well. But the interesting thing is if I play, particularly g, you'll see my tangent and normal line. But hopefully you can see that's what the tangent and normal are. The tangent passes next to the curve and has the same gradient. The normal is perpendicular to the curve. So as I float that, you'll see that the normal, which is the blue line, remains perpendicular to that parabola at all times. That's your definition. And just because we can, start them all, and then we'll move on. There we go. It's slipping out of it. Okay, cool. I'm going to leave that running in the background just for fun. So that's on there. You can follow that link to that, and you can have a play around with it as well if you want to. This is the other thing you need to recall, and it's something we talked about in Year 10. The gradient of the tangent is m. I've called it m1. Sometimes it's called mt. The gradient of the tangent is mt. Then the gradient of the normal is -1 over the gradient of the tangent. That's always true. So there's a couple of relationships, a couple of variations in this purple box or pink box. M2 equals -1 over M1 for perpendicular lines. M1, M2 equals -1. And we can go ahead and prove this. Those of you doing specialists, we can prove it using vectors. And there are other ways of proving it as well, but I'm not going to do that today. You just need to know those two things. So basically the three things you need to know is if you want to find the gradient of the point, you derive the function, substitute in the x value of the point. That'll give you the gradient. That will be the gradient of the tangent. If you want to find the gradient of the normal, use this process. And then use that linear function thing to find the normal or the tangent. And that's all of today's process. That's all we're going to be doing. So I'm going to do a couple of examples. Example 1. A straight line function has a gradient of -2 and passes through the coordinate 2, -5. What is the function? I'm going to give you 2 minutes to do that. Or aren't doing it. So a straight line function has a gradient of -2, passes through the coordinate 2, -5. What is the function? The process is that we start by saying y equals -2x plus c. You might get lucky and have this coordinate is 0,7 or something. If it's got 0, something, that's already the y-intercept. Your job's done, that's your c value. But usually you won't get lucky. Y equals -2x plus c. We know it passes through 2, -5. So I get -5 equals -2 times 2 plus c, which means that c is equal to -5 minus -4. So I subtract that -4 from both sides, and that gives me -1. And therefore, y equals -2x minus 1. Cool? Easy process. Make sure you know it. Example 2. If the tangent to a curve is y equals 3x plus 7, what is the gradient of the normal to the curve at the same point? So these are just stepped out type problems. I'll do this one with you. What is the tangent of this? What is the gradient, sorry, of this tangent? 3. Excellent. So the gradient, which I'm going to call mt, is equal to 3. And that comes directly from y equals 3x plus 7. It comes from this element, that function. So we know that to be true. The gradient of the normal, mn, is equal to -1 over mt, which is equal to -1/3. Yeah? Job done. Any questions on that? So that's 2 out of 3 of your processes. The third process is stuff we did last term, and earlier this term. Deriving, substituting the x value, and determining that situation. So I'm going to scoot down now and summarize, and then we'll do a couple more examples. You now have all the skills. You just got to put them into practice. So there's a bit of a summary, and you might want to come back and copy that down later if you'd like to. I'll leave that with you. But for now, we'll just do example 3 and example 4. Example 4 is a little bit trickier. So let's start with example 3, which is the whole process. Determine the equation of the tangent of that tangent. That's a good one. Of the tangent to the function y equals log x squared at x equals -3. Now, I don't know what log x squared looks like. I suspect it's going to look a little bit like a normal log function. That will be the overpowering element. But x squared is going to provide some sort of compression, but irregular compression factor. But I imagine it's going to look something like this. But because it's x squared though, remember we can't do logs of negatives, but we square it, so we actually get x squared becomes negative 3 squared becomes 9. So it does work on that side. So this might be, and I'm just making this up a little bit, but that's negative 3. There's our point there. You see, if my graph does look like that, I'm expecting my tangent to have a negative gradient, and I'm kind of thinking it's going to be somewhere pretty reasonable, somewhere near 1. It might be 10, it might be 0.1. I haven't got a very good scale here, but I'm not expecting it to be outlandish. So I've got a bit of an idea just by drawing a bit of a drawing that function and considering what a log function looks like and how this might apply. But let's do this now. So the first thing I need to do is determine dy dx, which hopefully you'll know is 1 over x squared. If I derive log of something, it becomes 1 over that something. But I have to multiply that by d dx of the inside function, which is x squared. And so I'm multiplying by 2x, and that becomes 2x over x squared, which becomes 1 over, that's wrong, 2 over x. That's my dy dx, which means therefore that the gradient of the tangent at x equals negative 3 is 2 over negative 3, or negative 2/3. And I said that it was going to be negative and somewhere near 1. This is negative and somewhere near 1. So I'm pretty happy with that result. You see a little bit of planning at the start though, which didn't take me too long, will get you an understanding of what to expect. So the question says though, determine the equation of the tangent. So I'm going to go ahead and do that now. And to do that, I'm going to recognize first that I have my gradient is equal to negative 2/3 and x equals negative 3. What I don't have is my y value. That's my issue at the moment. So I need to determine my y value as well. Y is equal to the natural log of x squared, and therefore y in this case is equal to the natural log of negative 3 squared, which equals the natural log of 9. And this would be a really good in the exam to test that thing that some people still find tricky. And that would be that some of you might still put negative 3 squared equals negative 9 and then try and do log of negative 9 in your calculator, and it doesn't work. So you've got to be really careful. When you square a negative, you get a positive. So we have the natural log of 9. So our coordinate is negative 3 comma log, it's not really log, 9. I'm going to create a bit more space for myself. Any questions about that so far? And remember our process is, this is step 1, find the gradient of the tangent. Step 2, find the coordinate if we need to. Highlight the gradient, highlight the coordinate. Now that I've got the coordinate and the gradient, finding a linear function is fairly trivial. Yes, albeit I've got a pretty horrible number here. 9 is not a nice number. I'm going to leave it as a natural log of 9 and keep it exact. And I encourage you to do that as well. So step 3 will be, step 3 might be to find the gradient of the normal, but this question is not about the normal. Step 3 is going to be to say, well, y equals mx plus c. So therefore, y equals negative 2/3 x plus c. And at x equals negative 3, y equals the natural log of 9. And so I get the natural log of 9 equals negative 2/3 times negative 3 plus c, which gives me 2 plus c. And therefore c is equal to the natural log of 9 minus 2, which is still positive but quite small. I believe it'll probably 0.2, 0.3, something around those values. But my function is y equals negative 2/3 x plus log 9 minus 2. And that's my linear function. And I can sketch that now. That will be a tangent to that curve. So you might go ahead and verify it, etc., etc. You'll see here, that's a fair bit of work that's happened in there, particularly to make my communication clear. You'll see also that I've got an irrational number here, so there's some added complexity there. Tangents and normal questions are really good for us. because there's something that you, if you put the work in the right way, you can make this a really trivial process for yourself. But because they involve multiple elements, we can make them complex familiar questions. So they're really great questions for you to get bonus marks, and as such, we will be setting questions in IA3 that are IA2 that are relevant to this, and they're bonus marks for you. You should be getting them. Are there any questions on this one? Okay, let's do example 4. We'll finish it off. Example 4, determine the location of the coordinate of the point of intersection where the equation of the normal x equals pi and 2 meets the equation of the normal x equals 3 pi and 2 for the function x cos x.